So the goal now is to turn this description in words, in plain English, into mathematics. And to get that going for you, let's just define xk. Oh, there we go. To denote the number of particles in the left urn at step k. Right, this is like a time step k. So k equals 0 with some initial configuration of these particles. And so here initially we could say there are 4 particles in the left urn, and then each time k gets incremented, right, time moves forward, 1, 2, 3, 4, k equals 5, 6, 7, and so on. Each time this time step gets incremented, I'm going to get up here, right, I'm going to pick a particle at random, I'm going to move it to the other urn, and so on and so on and so forth. And so, right away we have, a variable, and so you can start asking more precise questions. And I guess I left out some question marks, but what is the expectation of xk, right? That is a really common calculation, and this doesn't need to have anything to do with this particular urn model, right? Xk could be the winnings of some gambling strategy, some kind of risk that you're calculating, right? And so many applications you're interested in sort of expected value of things, and it's not completely clear how to calculate that yet, but we know, generally speaking, what an expectation is, and we know that if we have a random variable, at least, right, you can start trying to compute it, and follow up reasonable questions. Then, is xk a random variable, right? RV is what I'm going to denote random variables by, and so for now that's a question. May seem very basic, but you should try your hand at kind of answering it. And then we're in a class called Applied Stochastic Processes. So is xk a stochastic process? Right? How do you actually answer that in a precise way? And then if we think that x is random, and maybe it's a random variable, what's the distribution? Right? And once you get to here, then you can maybe backtrack to the expectation and start actually performing some calculations. Let me pull up, so this is kind of basics, but it illustrates an important point, right? So in our book, this is chapter 2 about random variables. I think Ross has it kind of just right. It's a little bit too short, so I'm going to try to maybe illustrate this description with an example. But if you look at the first paragraph at the end, he says here, these quantities of interest, right? So for us, xk is a quantity of interest, or more formally, real valued functions defined on the sample space are known as random variables, right? So essentially, Ross is pointing to kind of a definition of a random variable as a function from the sample space to something else. Here, it's real values, but in general, that's something is called a state space. So maybe you can read the rest of the paragraph while I kind of adjust a few things here, and I'm going to write down sort of x as a function from the sample space to the state space. So, all I wrote down was xk is a function from omega, which is what we refer to as the sample space, to S, which I would call the state space. We could try to discuss a little bit what these notions are for. So if we go back to to Ross's example or description, right? If you read from the beginning, it frequently occurs that in performing an experiment, we're mainly interested in some functions of the outcome as opposed to the outcome itself, right? So that's something I'd like you to think about, and I'm going to try to illustrate with in this model here. So essentially, our goal is to try to conclude that xk is a random variable, and it seems like that should be a pretty simple task. We just need to find the sample space, and we need to find the state space, and we need to establish that xk is is a function that takes values from here to here, right? And so one question would be, so what is the state space, right? That's essentially like saying, what values does xk take, right? So what are the possibilities, right? All the possibilities for the number, right, of particles in the left urn at step k. Well, a lot of it maybe depends on the initial configuration of the urn, but generally speaking, right, you could have no particles, you could have 1, you could have 2, you could have 3, all the way up to n, and you can't have n plus 1, right, unless the problem is allowing for some new particle to get created, but here we haven't mentioned that. So it seems reasonable to suspect that the state space here has a pretty simple description. It's just the number 0 through n. And then the next question is about the sample space and sort of what function is it even serving? Like what's the point of having a sample space at all? We have the state space, and we can kind of get a sense of the randomness in the system. What's the point of the sample space? So here I think Ross's description is pretty accurate, right? He's saying that we're interested in some functions of the outcome as opposed to the outcome itself. So the idea that he's trying to describe here is that the sample space may describe something very detailed, something very much outside of the experiment or the natural phenomena that we're describing. So, 0, 1, 2, 3 may be enough to keep track of the particles in the left urn, but it doesn't tell us everything about the system. Specifically, if I give labels to these particles, so I'll have 1, 2, 3, 4, 5, 6, 7, right? Knowing that xk was 3, it doesn't tell me which particle was where, right? And so this omega serves exactly this purpose. It's trying to describe, it's trying to give an elaborate, full description of the system. And xk is precisely sort of the quantity relevant to the experiment that you're performing or the natural phenomena that you're observing. And so let's try to give a description of the sample space here. So what do we need? Well, suppose we're trying to give a full description of the system. We basically want to say, we basically want to try to identify a state, right? Its states. And in this case, it will be useful to know exactly where particle 1, 3, and 2, and 6, and all of them are at any moment in time. And so one way of doing that is to just try to answer the question of, given some omega, which is an outcome, what should omega be in order to give us a full description of the system? And so maybe you can pause the video here and just think a little bit about this on your own. But I would propose that one way of doing this is to store this information exactly like a computer would. So a computer stores sort of ones and zeros, and that's exactly what we could do for every single particle. So I could, lay out all of these particles from 1 to 7, right? So these are kind of the slots. that tracks each of the particles, and then I'm just going to put a 1 or a 0 depending on whether that particle is inside the left turn, right? So for the left turn I'm going to put a 1, for the right I'm going to put a 0. So in that case I have a 1 here. I have a 0 for particle number 2, 1 for 3, 1 for 4, 0 for 5, 6 is where 6 is a 0, and 7 is a 1. So this is essentially a string of 1s and 0s that tells me exactly how the system is configured. Right? And if you actually sum up over all of them, you should see exactly 4 1s, which tells you what xk is. And what we've done right now is established, very rigorously, about as rigorously as you can, that xk is a function from the sample space to the state space. So let me write down this function. Xk of omega, right, and omega is in our sample space, is going to be equal to the sum of wi from I equals 1 to n. Right? What's wi? Well, wi is each one of these components here, right? So this right here is a w, or an omega, an omega 4, right? This is omega 7, and so on and so forth. So I've just demonstrated, kind of very, very precisely that xk is a function from this sample space, which fully describes, right, the state of the system, to a state space. And going back again to Ross's description of a random variable, and you should read the example that he brings up here. I think it's in terms of dice, but the general idea, at least as far as maybe say the sciences are concerned, that the sample space is describing in very much detailed what the full composition of the system that you're studying, whereas the state space and the random variable is pulling out only what's relevant. What's relevant here is just the number of particles in the left urn, right? I don't care where number 7 is. I just care that there are 4 guys on the left. And that establishes my function. Xk is equal of w is the sum over the omega i's. Keep calling w omega. It's omega, right? Omega is an element of the sample space. This is big omega, that's little omega. And so xk as a function of omega is just the sum of the components, right? And in here we'll get 4, and if I move one of those we'll get 3, and so on and so forth, right? So moving particle number 7 with probability 1 over 7 and landing it here will change this situation to this configuration, which is yet another element of omega, right? And that sum is going to now be 3, right? 3 1s, 3 particles. So I think that's about it, and the only thing I'll maybe tack onto this is exactly what omega equals in this specific example. It's denoted with this notation, and maybe you've seen it. Essentially what this means is all strings, or the set of all strings of length n with characters made up of the alphabet of 0 and 1, right? So that's exactly what it is. That's a string made up of 0s and 1s, and it has length n, and that's exactly what this is describing.